Okay, so welcome everybody to the iQuest seminar today. We're very fortunate. We have Jonathon Hood from Purdue University. He's at Purdue. He's been there since 2020. He has appointments in both chemistry and physics. And Jonathon did his PhD with Jeff Kimball at Caltech, a postdoc with Kang-Kwen Ni at Harvard before joining Purdue. And he has won an NSF Career Award. He has this really amazing result he's going to tell us about today. And so I'm very excited to have Jonathon here with us.
Okay,
so thanks.
Hello, thank you so much for inviting me. I have two experiments. This is a newer one that a lot of people don't know I work on. I haven't purposefully tried to keep it secret, but we published a result recently, and most of this talk is going to be focused on that. Also, it's organic molecules. I find when physicists see the organic part, they usually get really skeptical that we can do anything quantum with them. And so I partially hope to show you that these are actually really great quantum emitters. It's a field that I really am taking a lot from. It's been in chemistry since the 90s. This is when these molecules were first discovered to be lifetime limited. But there we go. Okay, so but really quickly, I do have two experiments. I have an ultra cold lithium cesium experiment. At the very end, if I have a little bit of time, I'll just tell you where we're at there. But the theme, if I had to put a theme on my research, it'd be molecules for quantum information. But these molecules are very different. Over here, we're actually trying to avoid using photons. The molecules have interactions when they're in their rotational states, and those are electronic ground, so they're very long-lived. And our goal is to get really long clearance times. In this experiment, we're working with dibenzotyrrolene. And when you cool this below 3 Kelvin, it actually becomes a great quantum emitter, even though it's a little surprising because it's just a bunch of benzene rings. It's really large. And in this experiment, we is to create photons. And so it doesn't have a spin, and we are really just looking at exciting it, getting the photons out, and then trying to create interesting quantum light sources with that. So the story will mostly be about the right-hand side. And just as a really quick introduction to superradiants and subradiants, you have a two-level system. The photon comes in, excites it, then it decays and you get a photon out. And a lot of the problem in light matter interactions is the fact that atoms are actually, they're 3D things. The dipole emission pattern for linear dipole is this donut shape. And if this shape was a Gaussian beam, our life would be so much easier, but it's not. It's a dipole emission pattern, and so it's really hard to efficiently couple light to these systems. And if I take this story a little bit further, I can talk about two emitters. And so now imagine that you have two emitters and they're very close to each other, close compared to the wavelength. They're oscillating in phase. And then if you look at the far field radiation pattern, they're going to be identical from each one. And then, you know, the electric field is going to add to each other. And so that means that power actually for a given amplitude goes up with that squared, so 4 times. And so this type of system is very good and very efficient at radiating power, radiates power much quicker than the single emitter. And then you have this complementary case called subradiance, where if you imagine the two emitters are essentially just overlapped and they're out of phase, then in the far field, you're going to deconstructive interference, and then it doesn't radiate any light. So it's a really simple concept of superradiants and subradiants. And if you look at the quantum picture, then you can associate this superradiant state with a symmetric combination of the two quantum emitters. And the subradiant state you can associate with the anti-symmetric state. Then to complete the picture, you have in this quantum model, this is called a Dicky ladder. You have this double excited state. And we're actually going to use the double ladder state a lot in our experiment, the double excited state up here. And in our experiment, we even do a 2-photon excitation. So we can send in 2 photons. You can kind of imagine it as it's a Raman transition at these levels, and we can get to the excited state. And then that excited state, this transition is subradiant both ways, and so it's mostly going to decay this way, and it emits 2 time energy correlated photons. And so you might ask, when you look at a level structure like this, you get this splitting between the symmetric and the anti-symmetric, and that's because the molecules are really strongly interacting. And how do you understand this interaction? Well, if you look at 2 atoms or emitters that are really close to each other, then they are going to feel the field of each other, and that causes a spin exchange, and so the excitation can swap between the 2 at some rate. We call that rate J. And in free space, the J scales with distance. This is distance between them over the wavelength, and you have in the far field you have this oscillation. In the near field, eventually you get to this 1 over r cubed potential, which is just really the dipole-dipole coupling when they're really close to each other. So there's been a lot of interest in superradiants. A lot of it has been kind of fundamental. In the 70s, that's when Dicky started looking at systems, many atoms that are coupled to each other equally. More recently, people have been looking at these arrays of atoms, and where they have to be sub-wavelength-spaced so that there's an interference, and they're looking at different geometries to see in which cases you have these superradiant bursts of light when you get what are the subradiant, what are the superradiant states. About 10 years ago, you had people looking at using the correlations between a lot of emitters to have superradiant emission, where the line width of the emission is determined by the atoms rather than the cavity, and so you can get really narrow output emission with the superradiant laser. More recently, people have been looking at the subradiant states, and the subradiant states are long-lived, so you might think that they're actually good at storing states. And so there's been a number of experiments exploring about how to put quantum information into the subradiant states. Recently, Emmanuel Bloch's group was looking at atomically thin mirrors of just a 1D array of atoms in square spacing, and showing that this type of system can be extremely good at absorbing a photon. So you get this enhancement from the superradiant effect. And then people even looked at all these subradiant states that are in the system. Well, they have interactions, and so you imagine you can send in light, put an excitation in the subradiant states, and then you get a lot of interesting many-body physics with all these subradiant states. In this case, Misha Lupin showed that you can have topological interactions, you can excite it into this atom array, and you can get chiral propagation. And then something that I'm kind of interested in is if you have now superradiant and subradiant states. So now imagine that you have a bunch of emitters and that you can send in light through a superradiant, because the superradiant state talks really well to the light. And then you can convert that to a subradiant state. You can do some manipulation of those states, and then you can eventually map that back to a superradiant photon out. And so people are also looking at this system for just doing arbitrary photon state generation. Okay, so it's a big field. A lot of people are looking into how to use superradiants and subradiants. And this is the topic that I'm really interested in, and that is multi-emitter, multi-photon. And so in this case, if you have many emitters, you continue the Dicky ladder, and you have at the very top, all the atoms are excited. If you can invert the whole system, then you're way up here, and then you'll make your way down the ladder, and you'll emit a lot of entangled photons. So when you talk to a theorist, they'll say this is a really challenging problem, because usually they like to treat photon modes that all have the same wavelength. But in this case, the photons, it's a highly nonlinear system. So what comes out has a lot of different wave vectors. And it's really hard to treat this theoretically. There was a really beautiful result in 2019 that showed if you just take superradiant light, which is kind of the simplest case. Superradiant light is when all the emitters are equally interacting with each other. Then if you send that to an interferometer, then the superradiant light can result in a Heisenberg scaling for measuring phase. So what that means is that if you send it into an interferometer and you're measuring the phase of one of the arms, then you can get a signal to noise that scales with the number of photons rather than the square root of the number of photons. And so a more popular version of this would be something like a Noon state or a twin Fox state or even a Fox state, which can get the Heisenberg scaling, get some type of enhancement. But it was shown that these all those examples would be cases where you just have a single frequency, a single mode. But this very highly entangled multimode state can also achieve almost the same scaling. And so now there's this really this open question that I'm really interested in, which is what other states can we make? And so the complementary way of making multiphoton states would be to use a single photon emitter, and then you can either emit several photons from that emitter, or you can multiplex afterwards to combine the photons together to make these large entangled photon states. But a natural way, another way to do it would be to just have many emitters. Somehow either invert the system or drive the system, you get a lot of light out. And then the question is, what kind of light can we make on the output? We now know superradiant light has really great scaling for doing intensity and phase measurements. What else can we make? Can we make cluster states using this technique? Can we just, the degrees of freedom we have are the spacing between the emitters. We can resonantly, we can drive it from the side. We can send in light that talks to all of them. And with those degrees of freedom, what kind of light can we make on the output? So that's the direction that we're going in this lab. And I'll show you today like the first step that we've made in this direction, which is just 2. But we are working with a solid state emitter. And so I'm going to give a quick overview on the requirements, because it's very strict on to see subradiants and superradiants with 2 emitters. It's only been done in the last 2 years with any solid state emitter. And here are the requirements. First, your emitters have to have the same frequency. Not really hard for atoms, but for solid state emitters, that's a big challenge. 2, they have to be spaced by much less than the wavelength. And that is just because if you imagine 2 dipoles, if you want to have full interference, they need to be much closer than the wavelength of light. If they're out here, then they're not going to have full constructive or deconstructive interference. That's actually really easy for us, but more difficult for atoms, because usually the lattice of your atom is half your wavelength. And so it's hard to get atoms really close to each other without having them actually collide with each other. And then the last one, which is a big challenge for us, is that you can't have any decoherence from the environment, because imagine this is our molecule, you have phonons. The phonons, I kind of imagine it as when the phonons are colliding or when the charges are swapping, then they're fluctuating frequency, and then that results in the photons that are emitted not being distinguishable. So, and so now if I just wanted to summarize what people have observed so far, this very simple case where you have 2 quantum emitters, you want to directly probe the subradiant and the superradiant state, prepare them. So far, there was a result in 2022, and this is a solid state. So atoms have done a number of complementary experiments. But in 2022, by Brahim Lunis, he had a great result using a different type of organic molecule, cooled down so that they were lifetime limited. And then he had a nano electrode underneath. And with solid state emitters, it's really hard to get top of each other. And so what he did here was he uses a nano electrode to put different electric fields on them. He tuned them into resonance, and then he could directly see the superradiant and subradiant state and prepare that. This year, by Peter Lodell's group, he had his first demonstration of this in quantum dots. And he did this with 3 quantum dots, but he only interacted 2 at a time along one of these 2D photonic waveguides, photonic crystal waveguides. And he used a magnetic field gradient to shift them into resonance. And so I believe the third result was ours also from this year, also with organic molecules. And the difference is that I really wanted to do this in a scalable way. I really want to get to a lot of emitters. And so we learned how to do it with light. And so we don't have any type of individual addressing in our system right now. So we shined light in, and then this is the result right here. You have a superradiant and a subradiant state, and then we learned how to tune them into resonance, which I'll kind of tell you how we did that. And they tune into resonance. You can see the subradiant mode disappears because the subradiant mode doesn't talk to our light. Okay, but now you might be asking, yes? I will actually talk about that a lot. Yeah, that'll be, in this case, we're doing something called light-induced tuning. So we turn on a very intense light. It redistributes charge in the crystal that, by a mechanism I'll talk about, we're a little confused about. It seems that if molecules are closely spaced inside a nanocrystal, then they tend to go onto resonance of each other. So it's decreasing the local inhomogeneous broadening. And if we keep pulsing this light, we can, a good amount of the time, bring two molecules directly into resonance. And so we're pulsing a very intense light, waiting tens of seconds, and then looking and looking and looking. Nope, which is the bizarre part. Okay, so out of those cases in solid-state emitters, only 2 of them were organic molecules. But I find it really interesting that in an AMO community, my background is very much atoms, ultra-cold molecules. Most people don't really know about organic molecules. So this next part of the talk, I'm just going to give a little introduction into organic molecules as single photon emitters, because I do really think they're quite powerful, complementary to quantum dots. So this is just a little overview. And again, Michel Barit discovered the molecule that we used in 1997. So this really isn't new. So here's how you can imagine this organic molecule. You have, and I had to look up a lot of this. This is dibenzotyrrolene. It's just a bunch of benzene rings. You have over here anthracene, which is 3 benzene rings. So imagine that you make a crystal out of this anthracene. We can do that in a chemistry lab, and we can make very pure anthracene crystals where all these crystals are aligned to each other. Then you come in and you take out a few of these anthracene crystals and you replace that with the dibenzotyrolene. And kind of similar idea to these diamond defects, where we're taking something out and we're putting it, and this dibenzotyrolene fits really well. It doesn't rotate. It has a homo to LUMO transition, which is at 785 nanometers. And it is a linear dipole moment. It's very linear. It has with solid state emitters, you usually have to, it's a little confusing. Some people call it zero phonon line. In this context, we call it a Debye-Waller-Frank-Connon factor, because if you go to the excited state, then it has vibrational states in the ground state. It also has a phonon sideband. And so you characterize it by how much of the light comes back down to the vibrational ground state and not in the phonon sideband. And for these molecules, it's about 50%. Compared to something like a nitrogen vacancy center, which is 3%, silicon vacancy centers also about 50 or 60%. And so it's comparable to this. If it goes to the vibrational ground state or the phonon, then within picoseconds, it relaxes right back down to our ground state. So this is a really good photon emitter in the sense that it is, well, actually, I'll give the numbers in a second. So now the remarkable thing is that if you take this and you cool down below 3 Kelvin, the phonon interactions freezes out. And this transition that I'm talking about, if you scan across it, it's 30 megahertz wide. So this was, to me, pretty incredible, because atoms, as you know, are 5 megahertz. And so it's just 5 or 6 times larger than an atom. But this is a molecule in a complicated molecule in a complicated crystal. Yeah. That's right. Yeah. It's actually really fun in the lab, because you can just rotate your polarization of your excitation light, and when you're orthogonal, it goes completely dark. So it's very linear. Yeah. 785 nanometers. Yeah. And also, you might think, okay, well, this is surprising for organic, and it is. This is the only molecule that has this property. There are a few cases that these anthracene, there's a few molecules that you can use for the lattice, and there's a few molecules that you can use for the emitter. Only probably 2 of them are very lifetime limited. And there is active research. They're trying to figure out ones that have telecom wavelengths. They're trying to figure out ones that have spin, because one of the reasons this is so quiet is it doesn't have spin. So it's a spinlet, both are spin 0. Okay, so I know there's a lot of photon people in the audience, and so I always get frustrated with like new quantum emitters that I'm learning about. I just want to see all the numbers, so I wanted to give you all the numbers right here. This is not demonstrated by me. This is demonstrated by other groups. And the purity of these molecules are below 0.5%, limited by jitter. The brightness, 250 million counts per second. That's much better than atoms, much better than NV centers, a little worse than quantum dots. And this is without any Purcell factor. The Frank-Condon to By-Wally factor, as I said, is 50%. And now 2 really hard experiments that I think demonstrate how good a quantum emitter is at how good the coherence level is creating indistinguishable photons. And so there's 2 ways people do that. The easier of the 2 ways is to use one emitter and then to send in separate pulses and then to get multiple photons out that way. And if you do that really fast, then if the decoherence is on a long time scale, then you can emit many indistinguishable photons that way. I think the record right now is about 100 with quantum dots in about a microsecond. And in this case, the organic molecules have, and then for those quantum dots, I believe that number is something like 98 or 99% indistinguishable. For creating indistinguishable single photons from a single emitter, the organic molecules are at 95%. A much harder challenge is to create indistinguishable photons from 2 different emitters, because then you need to cancel out the noise, the decoherence of both of those emitters at all time scales. And in this case, they've demonstrated 75% indistinguishability between 2 different emitters. Then they've coupled them to fiber cavities, had 95%. Yes. So then here is the number where I really feel like this system is lagging behind, and that is if coupling to a waveguide, a photonic waveguide, they've only coupled about 20% of the light, and quantum dots has demonstrated something more like 99%. And so coupling to I'll talk about the second half a little bit about our strategies for trying to couple this to photonic crystals, but this is where I think we're really lagging right now. Yeah. Yes. Yeah. I don't actually know a number. So I've never even seen anybody mention that before. But I do know that the transition is extremely linear. Like if we put our light in an orthogonal, we don't get excited at all. It goes completely dark. I don't know a number though. My guess would be it's good. Okay, but a huge disadvantage for the system is it has no spin. That's one reason why it's actually so good. It's actually more lifetime limited than a quantum dot naturally. Yeah. Yeah, me neither. Yes. Yes. I can't even answer that. I'm sorry. I don't know. But I mean, there is spin. I mean, there are singlet and triplet states, and there are triplet states in this system as well. It's actually really hard to calculate those for a theoretical chemist. So actually, one open question is, where is this state, and is it useful? Because a triplet state would be great. We could do gates. We could store quantum information in it. I couldn't give you a good explanation on where that spin is coming from. Yeah. Okay, so and then here another advantage. How do you make these? So we literally go in like the adjacent room. We have a chem lab there. We put the chemicals in a solution. We sonicate it. There's a nucleization process where these nanocrystals start forming. And then the nanocrystals are in a liquid. And then at the end, we just drop cast this liquid onto a substrate, whatever substrate we want. And it looks something like this. You have all these nanocrystals here. And then if we send in the fluorescent light, we can see, whoops, we can see all the different nanocrystals. So each one of these is one nanocrystal. We make them about, and so the molecule is pretty big. It amounts to about 10 million anthracene molecules. And then we can control our doping. And so we actually dope these 10 million anthracene molecules. We dope 300. And so what does that mean is if we take our TISAP laser and we scan across, we can see each one of these molecules. And so this is just scanning one nanocrystal. And each line here corresponds to a single molecule in this anthracene lattice. Then from before, if this is 782 to 784 nanometers. This is a huge range. And this is the problem in solid state emitters is that if your goal is to look for superradiants and subradiants, you have 300 molecules here and you need them to be resonant with each other. And so if your inhomogeneous broadening is about a terahertz or 100 gigahertz and you need them to be resonant within 30 megahertz, that's a huge challenge. Okay, so there's one other really great feature about these, which was just discovered a couple years ago by Costanza Toninelli's group in Italy, and that is also shift by light. Now, this is the only system where they have discovered this phenomenon. It is a permanent shift. You send in light, they shift. You turn off the light, they stop shifting. They're still investigating why this happens. I'll summarize what they think it is, but here's an example in our system. We have this, again, one nanocrystal. We have lots of molecules. This is the probe number, so we'll turn on an intense light. It shifts. We turn it off. We do the measurement, and you can see that a lot of the molecules are shifting. Some of them aren't. Or why it's binary. We're looking into that. But now you can see that there are some crossings here. So that's actually when we started this experiment, we were like, this is great. Let's just try to shift them into resonance, kind of go somewhere like here, and then we look for superradiant and subradiant between these states. Close to resonance, but there's actually not a, let me explain the mechanism, and then I'll actually say something contradictory to, because the current mechanism is that thought that you have a DBT molecule that it has, if you imagine, has two electrons, you double excite the electron goes to a neighboring pair, and then an electron from a lattice site nearby goes into it, and that creates a charge and a hole. That is a electric field gradient. And so that electric field gradient then, as long as these migrate from each other, then they have a really long recombination time, and then you get a static electric field. So that is the mechanism that I think we're pretty confident that that's what's happening, because if you have a molecule which has a quadratic Stark shift, then it only goes one way. If it has a linear Stark shift, it can go both ways. When we turn the tuning light on, we can measure the temperature and see that it's not changing at all, because these are actually really good temperature sensors. And in this paper, that she showed that these are this is a different type of crystal, but these are 5 different molecules that are very far apart, tens of microns apart. And she showed that you can, by tuning a different amount of lights, sending a different amount of light on each one, you can tune them all into a line. So when I saw that in 2020, this is kind of when I went all in on this system, because I'm really, in our community, we're really good at shaping light. And so I feel like, scaling this up, I could start to imagine a way forward. And so here's what we've done in the last 2 years. I'm going to show the spectrum a couple times. And here's how you can picture it. We have a lot of molecules in the system. We don't know if they're interacting with each other. It could be because they're far apart on the nanocrystal. It could be that they're completely different frequencies. But one early signature that we get that they're interacting is a 2-photon resonance. Now, here is that Dicky ladder. So this would be the double ground state. This would be both in the excited state. This is the symmetric. This is the superradiant and subradiant state. Although if they're not interacting, then this is just one molecule and this is just another molecule. And so then we take our laser and we scan across this area right here. And there is, in this case, you'll see here's one molecule. Here's another molecule. And now they are interacting. You look at a 2-photon transition, then it should have a quadratic dependence with power. And so this is what we set out to do. We were looking through the nanocrystal, trying to find this 2-photon resonance to see molecules. And the only way you see this is if they're close enough in frequency where they have a strong interaction. This is not superradiants and subradiants. I want to emphasize that because they are far detuned from each other. So this very much is one molecule. This is the other molecule. But this is how we get evidence that they are interacting. And our next goal is we need to tune them into resonance with each other because they're not resonant with each other yet. Okay, so, but even though this is an organic molecule, we do some Monte Carlo simulations with 3-level system, really simple simulation, and we get really nice agreement. So this is a plot where blue is the lowest power, and then we're gradually increasing the power. And so you can see that at the lowest power, there's no peak in the center, and then that goes up quadratically when you get to some threshold. And we can compare that to the simulation, just with Monte Carlo, and then we can take the widths of these and the heights, and then we can take it from the simulation, and we can see really good agreement. So it's a fairly simple system. You have to add, of course, the Frank-Condon Debye-Wally factor, these vibrational states that can decay to get this agreement. But it works really well. And the great thing is that we can actually repeat this many times. And so people have been looking for this in these nanocrystals for a while. What we did differently, and this was kind of luck, we discovered that if you turn on this light for a really long time, for an hour, at a very high intense power, 10 milliwatts focused down to a micron, then it seems that afterwards, if you look for these 2-photon resonance, you scan your frequency over the whole nanocrystal when you look for these signatures of 2-photon resonance, then you see them for a given nanocrystal about half the time now. And so now these are all different nanocrystals, and we can go in and we can see this is one molecule, this is another molecule, and there's a 2-photon resonance. That means they're close enough to where they're interacting, and they're close enough in frequency where we can see this 2-photon resonance. And we're even seeing really hints of 3-body interactions. So this is, for example, 3 molecules that are close to each other and interact with each other. So we saw a lot of exciting things. We can go to this 2-photon resonance, and you can characterize the output light, and you can see that it's bunched, and that's because it's emitting 2 photons. And then our next goal is to turn on the light and try to tune these into resonance. And so out about half of the nanocrystals we looked at after doing this really large pumping, we saw these 2-photon resonance. And now if we continue this process of pumping light, about half of these then tune right into resonance and stay there, which is somewhat magical. This is an example of a case. This was now this is at low power, so you don't see the 2-photon resonance. They're close enough where you start to see a height difference, and that means this is the superradiant one and this is the subradiant one. And then I am going to repeatedly turn on this intense laser, and you can see that they start to tune closer to each other. And then once they tune into resonance, you can actually see that the subradiant peak completely goes away. And that is because if you have 2 emitters that are, and the transition anti-symmetric, so that they're out of phase, then the light that you're sending in can couple to it all. And so it completely extinguishes. And so we can make a plot here of the detuning versus the asymmetry of the heights. We could also do this with the widths, and you can see that it nicely goes down there. And then where it goes to 0 is exactly what the J, the interaction rate between these 2 molecules. So then we can back out that this particular molecule has a spin exchange rate of about 250 megahertz. We can even, so this is the Dicky ladder, and we even, if you have molecules which are like this versus like that, then the superradiant one direction. So we can actually from this back out the orientation of the molecules relative to each other. And then what we're working on now is that you can, and Brahim's group showed this, that you can, once even though the molecules are really close to each other, in this case, they're 50 nanometers apart, you can excite the subradiant mode by sending in a donut beam, because a donut beam has an opposite phase on both sides. And so he showed in his work that he can excite the subradiant mode just to prove that it's still there. Okay, so when we get close, we can characterize these 2 states, because this is not convincing enough on its own. You really, we can measure the G2 of the superradiant plus and the subradiant stu and see that they're really modified, that these Rabi frequencies are greatly modified by this interaction. We can measure the decay time of both of them. We can see the subradiant state gets longer, the superradiant state decay is a lot shorter. From the ratio of these two, because you do a G2 measurement, what you're essentially measuring is once you get a photon, you're asked how long does it take to get a second photon? And when you're saturating the atom, that's essentially just the Rabi frequency. You're asking how long does it take to get back up to the excited state? So this really is just backing out from this, we get Rabi frequencies. And we can see that the superradiant state is greatly modified as we expect. But there's also decay into these other states, into the other vibrational states and the phonon sidebands, and those don't experience superradiance or subradiance, and so we can actually use the ratio of the lifetime in this to back out the Frank-Condon factor of the system, which in our case was about 0.2 and a little low compared to the normal 0.5. And, I think it's something to do with our synthesis. So now what we're working on is we've seen hints of three molecules that hasn't, I think, been done before in any system, including atoms, bringing three atoms together, three molecules together, three quantum emitters together, and then you should see two subradiant states and one superradiant state. So we're seeing some hints of that. So it just seems to be a really nice platform. But besides this kind of fundamental study, we're also really interested in this as a single photon emitter or a multiphoton emitter, and that kind of gets me back to the beginning of my motivation, which is I really want to have many emitters on resonant, send in light, and then get a huge burst of light out, and then try to engineer that light to do useful things. And so this is a cavity that we created in my lab, and we are working on ways to getting the organic molecules coupled to this, because to me, that is a huge limitation in the field. No one has successfully coupled a organic molecule to a nanophotonic circuit than 20% collection, whereas quantum dots have 99%. So my background is actually with these photonic crystals. And so what we're trying, we've demonstrated that we can actually take these organic nanocrystals and they fit within these holes. And so we've demonstrated that we can actually put them within the holes. And now we are trying to engineer the photonic mode. This is a 1D, but we're also doing it in 2D because you have a lot more degrees of freedom. We're trying to engineer it so that when you put a nanocrystal in there, then the Q actually doesn't get hurt at all. Because that's the big problem. Imagine you take this nanocrystal and you put it right here. Well, the nanocrystal, that surface is going to represent a really bad scattering effect. And so therefore the Q takes a massive hit, and that's what's limited the field so far. And so we're coming up with we're trying some methods where we put the nanocrystal in here, and then we're going to hide that nanocrystal with a material that has a very similar index refraction to that. The index refraction of these organic nanocrystals is 1.7. So it's not that, and the silicon nitride is 2. So it's kind of optimistic that we can put something similar to 1.7 and then hide it so that there's not this scattering interface. But that's the big thing we're working on right now. And then I'd like to, in a couple of years, it seems like in the single photon emitter community, these chiral interactions are really important for certain protocols. Don't have because they don't have spin, so it's always a linear dipole moment. But it seems like to me the quantum dot communities also kind of move in this direction, where you make topological photonics so that the conditions coming from the photonics rather than the chiral properties of the emitter. And so I think this is a great photon source for exploring things like this. And then finally, there's kind of this going back to how are we going to do this with many molecules? And there is spectral wandering, and the experiments that we did, we picked wandering that have even no observable spectral wandering. But if you imagine there are charges in this nanocrystal, and so some molecules have this wandering effect, where the charges are kind of moving around in the nanocrystal. It has a Stark shift, and so this is data from one nanocrystal, and we have three molecules which are very close to each other. And what we found really interesting about this was that these two molecules had a 2-photon peak. And what that meant was that they're about 30 nanometers apart from each other. 30 nanometers is really small. So the hope is that at 30 nanometers, they're experiencing the same decoherence. So the interaction with the charge, interaction with the phonons should be similar. And this is another molecule in the same far away, and there's no correlation. So what we're also working on, and I think this is unique to this system, is if we can find two molecules that are really close to each other, 10 nanometers apart, can we use one of them that's the sensor, purposefully not tune them into resonance, and one of them the emitter? And then how well can we cancel out the decoherence? Especially if we have this coupled to a photonic crystal cavity where we have really high resolution, where we can send in a single photon and get a quick signal about the noise is doing, and then do feedback with either an AC Stark shift or with an electrode or something like that. Hopefully, it's already a fairly lifetime limited, but the hope is that we can push this up a lot more. And this is something you really can't do with quantum dots, just because quantum dots are large. It would be very hard to get them to experience the same inhomogeneous broadening. So this is something that we're going to work on. And then also kind of my dream here is going back to these arrays, where we've started making these co-sublimated crystals. And so I've been talking about nanocrystals so far, but this is actually a crystal of anthracene, which is about this is a millimeter. So this is a massive crystal. It's super pure. We made it with this co-sub chamber that one of my students made, and with help of our instrumentation facility in the chemistry department. And really pure. And so what that means is that the line widths are actually even better here. The inhomogeneous broadening is about an order of magnitude smaller, and we can dope them with a lot of molecules. So the hope is that kind of complementary to atoms, instead of having to place the atoms in an array, put an atom every place, let's just dope it so that we have these organic molecules everywhere we want them in some type of configuration, sub-wavelength configuration. And then we come in with light, and then we try to tune all of them into resonance. We can try to do this active cancellation and try to get an array. And I think for a lot of the effects that we're looking at, you don't need to get them perfectly into resonance. I think like the demonstration Costanza did, where you get them about a line width and a half, would be enough to see some effects we're looking for. And why I'm kind of optimistic about this is that in atoms, when you try to do a sub-wavelength lattice, you have this problem where, for example, tweet. We can have molecules separated by 600 nanometers. And to tune them into resonance, we don't need to take a Gaussian beam and focus on each one. We can actually, all we really need to do is have a super high intensity. And so if we intensity gradient. So if we have a large intensity gradient by using some super resolution imaging techniques, we can actually send a very different intensity for two molecules that are 600 nanometers apart and try to tune them into resonance. So I'm optimistic about this because we aren't really limited by the diffraction limit in this case. And so getting a large array, sending in light pattern by a spatial light modulator, trying to get a large array into resonance, it hopefully won't be too hard. How much? Okay. Maybe I can take questions about this, and then if we have time, I know it's a lot to switch experiments. But yeah, I'll take, yeah. Superradiant, what, sorry? Yeah. Yeah. Yep. And Hirosh talks about this in his essay of superradiance. Yeah. Yeah. So Humboldt Rich had looked a little bit into this. What configurations can you get where the dipole-dipole interaction, the near field interaction, don't in subradiants? For example, a ring works. A random array, a random place atoms doesn't work. In the case I was talking about earlier, we have a single nanocrystal and a lot of molecules. When we start getting to 3, 4, 5, hopefully, it will play a very important role, and we'll actually be looking for those types of effects. For this type of system, it won't really be a deal because they're really far apart from each other. I mean, these will be lambda over 4, lambda over 5 apart from each other. I think Hirosh calls it van der Waals to phasing. Yeah. Any other question about this? Yeah. This one?
So on the y-axis was this one particle gives metal one plus P, and the y-axis was quite similar to another metal. My question was, what is the power or time required between them? How does it scale as a function of n, where n is the number of molecules you want giving signal? So like for n molecules, what is the time required between them, or the energy required? How does that scale?
Okay, so let me try to explain. So there's kind of two ways to tune that I've mentioned in this talk. One would be if you could individually address the two molecules. In this case, we're not doing that. We're sending light in. So there is a huge amount of inhomogeneous broadening in the system. Go back. These are 300 molecules spaced over 2 nanometers. When we turn on a really intense light, we do not see a decrease of the overall inhomogeneous broadening. What we do see is that molecules that are close together, tens of nanometers, have a decent probability, about 1 case per nanocrystal, of coming right into resonance and staying, which is extremely improbable, unless there's something happening. And in this case, we're attributing it to, it has to be that the two molecules that are close to each other, initially they're far apart, maybe because there's a charge nearby, and so they're seeing a different electric field. We think what's happening is that when we have a high intense laser, it's causing a lot of charge migrations. The charges are maybe accumulating on less defects, and so therefore the electric field noise correlation length becomes a lot longer, and so then molecules that are close to each other tend to go in resonance. Now, how long does that take? An hour to get them into resonance, and then they stay in resonance, and they don't keep shifting. And it doesn't. You asked about like 3 or 4. We don't really have control over that. Yeah. Because we don't have, we're just shining light and just seeing what happens. Yeah. Yes.
Have you any clue as to why it goes to some and why it doesn't for others?
Well, the tuning mechanism?
Yeah.
Well, because there's different sources of inhomogeneous broadening. There's also strain, charge. So if strain is the issue, that the two molecules are unresonant, this is not going to work. So this is really like has to be a location where there's not a strain difference between the two molecules. Coupling to the phonons are similar, and then the charge migration seems to work. So yeah.
So I'm understanding correctly, we're expecting that some of those lines overlap.
Yes. I have no idea. That's not something we've tried. We've heard things change a lot when you go up and down. So I don't know. I probably suspect not. Any other questions? Yeah. When they're into resonance, you don't really get a 2-photon resonance anymore. I mean, it's technically still there. It's just really hard to distinguish because the width of it is going to be similar to the separation between the superradiant state. So no, that we haven't really seen that. Now, when you see something like this, actually, I'm not a big fan of this figure because it doesn't really show things coming together, because we've only observed it a handful of times, and we're usually like zoomed in on 2 molecules at that point. But even in this case, you could still say these are crossing each other. Maybe they stay together after, but there are definitely still crossings. But what we're seeing is that even if we shift for infinite time or a day, they stay. Once they come together, they stay together. So there's some mechanism where they're experiencing at the same time. Any other question? Yeah. Sorry. Yeah. Yeah. Please. So those are actually the same. Yeah. So if you have 2 emitters and calculate the total radiated emission, then when they're much closer than the spacing of light, then you'll see that superradiant one gets enhanced, subradiant one's not. You can also picture it as that you have 2 molecules, and the molecule has a electric field. It generates electric field. And so you can also do a calculation to see how much power is being lost by doing a E dot electric field dot current, where you kind of represent this dipole as a current. And those give the same answers. When you do calculations, I always do the E dot J because it's a lot easier to calculate the electric field from, we would call it Green's function, than it is the integral for power. Well, it's just power, it's energy conservation. Yeah, energy conservation, right? I mean, the energy is either in your system or being radiated in the far field. That's, yeah. Yes. Yes. So, I mean, technically, when they go into resonance with each other, there is some interaction. It might, if the molecules are 300 nanometers, 400 nanometers away, it's a very small interaction. It's just hard to see. In our experiment, the ones that are really obvious are the ones that have strong interaction, and that doesn't happen at all. Yeah. Yeah.
So in that case, expected critical density doping where you get the
great question, and that's what we're curious about. Yeah. So what we're trying now is we've seen some hints of 3 body, but we think we might be able to increase the doping by 5. If we go up a factor of 5, there should be a lot. After we do this tuning, there should be a lot more interaction. But at some point, the molecules are going to be, there's going to be so many molecules that the lattice itself is going to start being less pure, and then you're going to have some problems with, in fact, this might actually be one of the reasons why our Debye-Waller Frank-Condon factor is smaller than we've seen in other systems. So there could be some detrimental effects for having high doping. Yeah. Yeah, I won't go on to the next part of my talk just because I don't want to, yeah, we're getting close, yeah. Yeah. Okay. Yes, yes.
Would you instead design one giant molecule, which is basically like the thing that emits being
and the chain being, so I think we were calling, I think have done this, they would call it a dimer, and that's where you have 2 molecules that they actually bond together very weakly. And in those cases, yeah, you have an extremely large interaction. I'm not sure. Yeah. So the idea, if I kind of go back, because this is something I was thinking about earlier on, get them a 2-square array, and there is some proposals. There's Sandig Dar did a clever experiment where he kind of was able to use an electrode, nanoprobe tip, and kind of deposit the molecules with about I think 20 nanometers resolution, so he could make a square arid. But I don't really want to do that. If you think about it, you know, even in a nanocrystal, which would be like a micron large, we have 300 molecules. That means at this level with this large crystal, we're going to have molecules everywhere we want them. So it's just a matter of tuning those molecules into resonance, and then hopefully the other molecules which are out of resonance don't play. But you know, I hadn't actually thought about that. At some level, they play it. Yeah, yeah, sure. That's a little too much out of yeah. I'm trying not to get too involved in some. Okay, if that's it, then I think I might just go to my last slide. And yeah, so this is work done by 2 people, Christian and Emma, who are both 3rd years. And it's been kind of fun because half my lab is chemistry and half my is physics, and so it's interesting to see them talk to each other and try to learn the same language. And then the other students, postdoc, Smitra, Carl, and David are on the other experiment. And then this work is done with Valentin, who some of you might know. He's in the quantum optics theorist. He helped, and then Li Bai Huang is a chemist in my department who's helped. Thank you.
For a great talk, and then there's one.
Great.
We will get you to the front one.